In this video, we described the effect of the electronic environment on NMR spectra, and we also talked about the chemical shift. Right, so if we try to then predict what the NMR spectrum for a very simple molecule would look like with what we know until now, okay, we could say that, well, we know that the frequency at which we expect radio frequency photons to be absorbed is going to be equal to the Euromagnetic ratio, then the external magnetic field, then over 2 pi. All right, so what that means is that for a molecule as simple as ethanol, okay, we should expect to find one peak for the NMR active nucleus in the molecule, which in this case is proton. Okay, notice that that will be C12 mostly, so we're not going to be worrying about those carbons. Oxygen, we're not going to worry about it either. So again, the only NMR active nucleus of interest to us in this molecule would be the proton. And again, according to this, we plug here the Euromagnetic ratio of the proton nucleus, and then the external magnetic field that we applied, we would expect to find just one peak. Okay, however, that's actually not true. When we take an NMR spectrum of the ethanol molecule, we actually see 3 different peaks. We see a peak for this proton, we see a different peak for a different signal for these 2 protons, and we see a different signal for those 3 protons. Okay, so there's 3 signals, and again, these correspond to different groups of protons. The question is why? What is the mechanism that gives us that discrimination of the various protons or groups of protons in the molecule, okay, which is so essential for NMR spectroscopy? Well, it turns out that the electronic environment has an effect on the signal. Okay, when you put a molecule in an external magnetic field, the effect of the magnetic field on the molecule is going to be to induce some electronic currents. Okay, there's going to be electrons moving, okay, as a consequence of the magnetic field. And every time that you have an electronic current, there's going to be a magnetic field that is generated by that motion of electrons. Okay, so that magnetic field that is due to the motion of electrons might oppose or add to the external magnetic field, depending on what electrons are around. Okay, so for example, here, for that proton, what we actually have is that the electronic environment in the vicinity of that proton is that you have an oxygen atom being a nearest neighbor atom. Okay, so the electrons of that oxygen atom are going to generate a magnetic field that either adds or subtracts to the external magnetic field, okay, to generate a local magnetic field that is felt by that hydrogen atom. Okay, however, these 3 hydrogen atoms, these 3 protons, don't have an oxygen atom nearby them, right? The electronic environment of these 3 protons is actually different from that. So it turns out that the external magnetic field experienced by these protons will be slightly different from that due to that proton. And the same thing can happen for these H2s, where again, you will have here a neighbor that is an oxygen, but you also have a neighbor that is a carbon, right? So again, notice that the electronic environment of that proton, those protons, and those protons is different, and that means that it will give rise, you will see 3 different signals. A way to quantify that is to modify this expression to say that this expression actually, when you have a real system with electrons, okay, like we will have right here, not a bare nucleus with no electrons, okay, is simply going to be 1 minus sigma, okay, where this is called the shielding constant that is due to the electronic environment. Okay, so again, the idea is that this shielding constant is going to be different for this age, for that group of protons, and for the group of protons, because this depends on the electronic environment, and the electronic environment of that, and that is actually different. Okay, so again, what that means is that you are actually going to observe 3 different frequencies of photons that you need to shine to in order to excite those nuclear transitions. Okay, right. So actually, the way that we represent NMR spectra is not through the plotting here these frequencies of the photons. Instead, we're using something different, which is going to be something that we call the chemical shift. Okay, so when you think about NMR spectra, what is in the x-axis is not the wavelength of the photon or the frequency of the photon or the wave number of the photon. There is something that is called the chemical shift, which we call delta. And the question for the chemical shift is simply this. the resonance frequency that we calculate from that expression, and again this is sensitive to the electronic environment, minus the frequency, the resonance frequency of a reference, okay, which everybody agrees on, divided over the resonance frequency of the reference multiplied times 10 to the 6. Okay? So for proton NMR, what happens is that the reference is equal to a molecule that we call tetramethylsilane. Okay, so a molecule that looks like this. Silane with 4 methyl groups. Okay, it has tetrahedral form or tetrahedral shape. And it turns out that all of these protons have exactly the same electronic environment. And that means that you actually need a very little amount of this molecule to get 12 protons that absorb at exactly the same frequency. They're going to give you a very intense signal. Okay, so again, the idea is that when you do an NMR spectrometer, you put this as a reference, and then you measure what the frequency of your molecule is with respect to the reference, and then compute the chemical shift like this. Now, the question is, why do we want to use this expression as opposed to just use the frequency that you actually get from here, the frequency of the photon? Here's the advantage of using a chemical shift. The chemical shift is a relative measure of the properties of the photon. Okay, and this frequency is actually an absolute measure of those photon frequencies. The problem with using the frequency directly is that it depends on the external magnetic field. So that if you measure this molecule in a external magnetic field of 2 Tesla or 10 Tesla, the frequency will be different, okay, because it's affected by the external magnetic field. And again, not everybody has the same external magnetic field, and that would make it very difficult to compare spectra taken in different spectrometers. However, the chemical shift, okay, because it's a relative measure with respect to a reference, okay, and it kind of cancels out the effect of the external magnetic field. The chemical shift does not depend on the spectrometer, the external magnetic field that you actually apply, okay, and that's why it's a much more useful measure of the photon properties that you need to shine on the molecule to excite the nuclear spin transitions. Again, if you were to use the photon frequency, that would depend on the external magnetic field, not very useful for comparison. Okay, instead you use the chemical shift, which is a relative measure, okay, and is independent of the spectrometer. Okay, so there are tables in the literature that actually show you what the chemical shifts for various protons, depending on the electronic environment where you expect to find them. Okay, so we have that alcoholic protons, okay, have a different chemical shift than these protons, which are aliphatic, and those protons that are aliphatic but are neighboring an oxygen atom. Okay, so again, there's extensive tables, and you can look for where you expect to find different chemical shifts for various electronic environments.